Hello, everybody. This is a quick review of what we did in class on emission and absorption lines. Emission lines is when you have the energy levels of electrons in any atom changing from one level to the other. Specifically, emission is when electrons fall down to a lower, more negative. Remember, lower means more negative state or energy. So for instance, from the n equals 2 to the n equals 1 state in hydrogen, so the example is hydrogen, but this is true for any element, as we're going to see. Each of them has different energies, but they're quantized, meaning the energies are exact. Exact levels, or quantized. So the n equals 2 to n equals 1 corresponds to a delta energy 2 to 1 of the ground state, right? So the ground state E1 is negative 2.1802 times 10 to the negative 19 joules. The nth state is that number, which I'll just write as E1 over n squared. And lambda is going to be hc over delta E, where delta E is given by the difference between any two states. So these are the equations we're going to use for hydrogen. I'll give you the values for other ones, but I'll show you where they come from. So E2 to 1 will be E1 minus E1 over 4, or E1 over 2 squared. And I'm just going to do absolute value here, just to make it easy. So I'll do bigger minus smaller, absolute value, 2.1802 minus 2.1802 over 4, and I get a value of 3/4 E1, which is kind of a fun shortcut. So I get 1.635 times 10 to the negative 19 joules. Now you might notice this is in the ultraviolet. If you take out your table, you take out your spectrum, that's why we did that. If you solve for the wavelength, you get a wavelength of 121.8 nanometers, or 1.218 times 10 to the negative 7 meters, if you use this formula. That's it. The Balmer lines are all indivisible. They are transitions to the n equals 2 for hydrogen. Neater. Just a little bit. When we have n equals 5 to 2, 4 to 2, 3 to 2, 2 to 2, or even 6 to 2, 6, 5, 4, 3, 2, when the electron falls down, it loses energy, and that energy is emitted in terms of a photon. By the way, gamma equals photon as a symbol. Obviously, E negative is electron. Gamma, typically, gamma particle is a photon, is a particle of light. So what are these wavelengths? Well, the wavelength 3 to 2 is going to be hc over delta E 3 to 2. And delta E 3 to 2 is going to be E1 over 4 minus E1 over 9. Again, absolute value, just because we want the energy of the photon. We know the electron lost this amount of energy. This is also the amount of energy the photon gains. If that makes sense. You can pause and replay that if that conceptually doesn't make sense. The electron's falling. It gives the energy to the wave in the electromagnetic field, like dropping a rock into a calm pond. It's going to create ripples in the calm pond, right? And the amount of energy it has determines the energy of the ripples. Now in a pond, that energy is probably amplitude, but here the energy is frequency. So you have a larger frequency for a higher drop. Again, I said that in words. See if you can make sense. So this is a larger frequency than this, which is a shorter wavelength. That's the connection we want to make. So either way, we get that this is going to be E1 over 4 minus E1 over 9, which is 5/36 of E1, which gives me 3.028 times 10 to the negative 19 joules. And I just realized my last slide, that's supposed to be 18. This is supposed to be 18. Many sorries. And this will give us negative 19, which is indivisible. So this, if we actually calculate it as a wavelength, is 656.46 nanometers. Or if you did it directly, you would get 6.5646 times 10 to the negative 7 meters. Which is also 6564.6 angstroms, which we're going to want to get used to as well. But here we go, there's the energy and there's that. And so you can do the 4 to 2, the 5 to 2, and the 6 to 2. I'll just write the answers out here. 4 to 2 is 486.1 nanometers, which is 4861 angstroms. And 5 to 2 is 4340 nanometers, which is 4340 angstroms. I think it's a 0. And then 6 to 2 is 410 nanometers, which is around 4100 angstroms. There's names for these, which is kind of fun. This is called H alpha, because it's one of the most prominent lines. Remember that red line we saw when we looked through the diffraction grating at the hydrogen gas? That's this. It's exactly this wavelength, which I think is amazing. So the electrons are being excited by the electricity, by the electric field that, plugging it into the wall does. That device excites the gas. The electrons get excited, and then they cascade back down. They get unexcited, and they lose the energy. So the electrons start off excited because of the input of electricity or the input of an electric field. And then when they fall back down, that energy turns into light, electrical energy turning into excited electron energy, turning into light energy. This is called H beta, H gamma, not photon, gamma as in alpha, beta, gamma, the first 3 letters of the Greek alphabet, and H delta. And there's actually an H epsilon, you can keep going. But these are the 4 most prominent Balmer series lines, and you notice they're all indivisible. These are a nice violet, not ultraviolet, but you can actually see them. Violet, this is a nice cyan, or like a blue-green, like a cyan green. And this is a nice red. Right there. Isn't that cool? So you can actually see these. So that's emission. What's kind of cool is that we can look at different elements and we actually see different things. So for instance, there we go. If we look at helium, helium has a lot more transitions than hydrogen. Here's some of them. right? There's a lot more going on just because there's 2 electrons and you have to include quantum mechanical effects. You actually get one of the most prominent ones is at 587.5. So helium lamps glow yellow, kind of a yellow-orange. So that 587 is similar to the 656. The 587 is, let's see, where is it? It's between the n equals 3 and n equals 2 state, but there's actually, it's the 3d to the 2p orbital you might have learned about in chemistry. That's the most prominent one, and there's actually a shift down from what normally would be 656 is actually 588 nanometers, a little bit higher energy than the 656. And you get some red lines in helium, you get some cyan, you get a few more lines, and it actually looks like this in a diffraction grading. We'll do this in class. There's some other fun ones. Hydrogen's here, look at helium, there's neon, there's sodium. Sodium, you basically get yellow. Sodium lights are used on streets. The entire city of Chicago glows yellow. Europe is transitioning from sodium lamps to LEDs. So from space, it looks white instead of yellow, which is amazing. And then here's mercury, which are typically used in fluorescent lights, like the ones we have in the classroom. Here's carbon, oxygen, nitrogen, iron. Oxygen is a really important one. Oxygen occurs in certain nebula. So if we look at the Orion Nebula, take a look at this graph. This is a graph of emission lines. How do we know it's emission? Because there's nothing and then there's a spike. Nothing plus spike is emission. So I get the H alpha here. Do you see that one? You see the H beta, 486, H gamma, 434, H delta, 410. Right, find those. And then oxygen 3 is 500.7. I'll give you these numbers eventually, but oxygen 3 is that. And oxygen 3 is also 495.9. I had to look at my sheet, on my little bookkeeping sheet. You notice helium 1 is there at 587, although they didn't draw it orange or yellow. There's a little bit of helium in the Orion Nebula. Right? A little bit of nitrogen, right? So these lines tell us what's there. We can zoom in and tell us what's there. So that's emission. The difference between emission and absorption is pretty easy, right? So absorption comes from when you have a source behind a cold gas and the gas absorbs those transitions, right? So when we're dealing with emission is just a hot gas or an electrified gas emitting those lines. But if it's not emitting it on its own, I can have a continuous spectrum like a light bulb behind it, and it absorbs it. A great example is the sun. So the sun, through its atmosphere, emits a continuous spectrum that's absorbed. So only exactor colors are removed from an absorption spectrum, which match the lines that would be emitted in the emission spectrum. Notice that the lines match perfectly. It's just here they're emitted, here they're absorbed. So here it's like nothing and then lines. Here it's everything and then black spots. So literally they're opposites. If I put this in here, it would complete the picture, right? So you need a cold gas with a light behind it. Now the atmosphere of the sun is relatively cold compared to the sun itself. So the sun's a great example, and the sun has actually lines called the Fraunhofer lines, which tell us the atmosphere of the sun. The water, I think, is actually from our atmosphere. Some of these are actually from Earth, so we have to be careful what Earth is taking out. But the water might be in this. This one might have. I know there is some water in the sun. I can't remember if this is including that or not. But either way, we have. Look at these little absorptions. So absorptions are dips with a continuous behind it. Emission, right, is spikes, right? So absorption is dips. Emission is spikes. Pause and make that make sense. I hope that makes sense, right? So here's an absorption line of hydrogen, where there's a continuous spectrum, notice there's a lot of things going on. There's like a curve here, and then you take something out. Here, there's nothing, and then you add something. So that's something emitted. Here's something absorbed. But notice how it matches at here 656, right? Here's a continuous star with hydrogen in it. And here, I don't know if we can see the Fraunhofer lines, find 656, that's C, that's hydrogen. There's hydrogen in the sun. There's actually a lot of hydrogen in the sun. The reason the dip isn't so big is because it's actually not hot enough to excite the electrons. So hotter stars actually excite electrons more, as we're going to find out when we study stars. Oh, here's the Orion emission spectrum. We got some oxygen there, nitrogen, et cetera, et cetera, et cetera. There we go, right? That's it. Look at that. It's fun. We can see what the universe is made of just by looking at the light. I hope that made sense. Absorption versus emission and calculating what the lines and the energies are. Thank you, friends.